Welcome to this explainer. So, if you follow AI news, you've probably noticed a pretty frustrating trend. Current LLMs sound absolutely brilliant right up until you throw a basic what-if question at them, and then, total breakdown. We are constantly looking for ways to fix this fragility. Well, today, we are breaking down a major paradigm shift that finally moves language models away from implicit correlation and towards explicit, auditable reasoning. It's a completely fresh approach to causal inference, and it really has the potential to fundamentally change how we build question-answering systems.
Here's our roadmap for today's explainer. We're going to start with the core LLM reasoning problem, introduce the new Causal-Audit framework, dive into how it constructs target-aware graphs and aggregates path-level evidence, and finally, wrap up with what this means for AI developers and how you can actually implement it.
All right, let's jump right into Section 1, the LLM reasoning problem.
To really grasp the solution here, we have to look at what's fundamentally broken in current AI pipelines. Traditional models generate answers using end-to-end language modeling. Basically, they rely on latent attention to just sort of guess at cause and effect based on patterns. It's kind of like a student memorizing the answers for a math test without actually learning the formulas, right? This implicit approach is a major issue because it completely conflates direct causal links with statistical noise and confounding factors. If you're just matching language patterns, you aren't actually isolating variables.
As the researchers behind this new paper clearly point out, this whole implicit guessing game creates a massive black box. You end up with opaque causal assumptions and reasoning paths that you literally cannot verify. The system just falls apart when you ask intervention-based questions. You know, the what happens if X changes scenarios. This is especially true in context-free settings where the model doesn't have external grounding to lean on. The results? Super fragile predictions, simply because the model doesn't actually understand the mechanics of the system it's talking about.
So how do we fix it? That brings us to Section 2, introducing Causal-Audit.
Researchers Su Lan, Shufei Yin, Yanming Zhu, and Alan Wei-Chung Liu recently submitted a massive structural rethink to the Association for Computational Linguistics for 2026, and it's a real game changer. Causal-Audit completely abandons that implicit prediction we just talked about. Instead, it shifts to explicit graph-based reasoning. It swaps out the end-to-end black box for 4 distinct modular stages: graph construction, constraint application, path evaluation, and evidence synthesis. And because it's modular, every single decision path is fully auditable and traceable. It explicitly filters out the noise right from the start rather than trying to slap a post-hoc correction on it later.
But wait, how do you actually build a causal graph that doesn't just evolve into a giant, tangled mess of associations? Let's look at Section 3, Target-Aware Graph Construction.
This is absolutely crucial. Traditional graph building usually gives you these dense, unfiltered networks packed with weak associations. Causal-Audit bypasses this by using what they call a target-aware constraint strategy. Think of your target variable like an anchor holding a ship steady in a crazy storm. By using that target as a fixed anchor, a core constraint, the system aggressively prunes out all those training data artifacts and irrelevant nodes before they can dilute the actual reasoning signal. Basically, if a node or an edge doesn't contribute to a valid causal path pointing directly to that anchor, boom, it gets suppressed immediately.
Now, once you have that cleanly constrained graph, the model still has to actually reason through it. Let's explore that in Section 4, Path-Level Evidence Aggregation.
So we have our clean graph. Now, instead of relying on one fragile chain of thought, which, as we know, is a classic failure point for traditional LLMs, this system evaluates multiple valid paths all at the same time. It looks at both the reinforcing causal effects and the counteracting ones across all these paths. Then, it synthesizes all those signals into one unified causal score to determine the final answer. This is brilliant because it completely prevents a single flawed chain of reasoning from dominating the decision boundary. It makes the decision-making process incredibly robust.
Okay, let's translate this into real-world utility in Section 5, AI development and traceability.
This shift from implicit to explicit completely rewires the development stack. In a traditional setup, what do you get? Output probability, confidence scores. But with Causal-Audit, actual traceability replaces those standard confidence scores. Because the architecture explicitly separates the building of the graph from the evaluation of the path, you, the developer, can look right under the hood. You can directly inspect intermediate states, verify the graph topology, make sure constraints are being followed, and actually audit the exact path aggregation weights to see exactly why an edge was kept or tossed.
And because that noise suppression happens explicitly before the reasoning even starts, You can finally say goodbye to writing paragraphs of prompt engineering just trying to stop the model from hallucinating links. This framework is specifically designed to handle context-free settings. That makes it a powerhouse for things like synthetic reasoning tasks, controlled simulations, and code dependency analyses. In fact, the paper shows this framework consistently outperforming existing LLM methods across 3 major benchmarks that are specifically designed to test complex variable shifts.
Now, to be fair, every major architectural shift comes with trade-offs, and we need to talk about them. The researchers are upfront about a key limitation. This explicit 4-stage pipeline definitely introduces real computational overhead, compared to just letting an autoregressive model spit out text. Plus, if you're building real-world apps that need dynamic context injection or multimodal grounding, you're going to need extra adaptation layers. So as a developer, you have to carefully weigh that need for absolute audibility against your latency limits and resource constraints.
But if intervention accuracy is non-negotiable for you, let's look at Section 6, Implementing the Framework.
Integrating this isn't just about tweaking a system prompt, it's a structural overhaul. First, you've got to map your queries to identify exactly where causal isolation is needed. Then, explicitly define your target variables in your query schema. Those are your anchors, remember? Next, you inject constraints to prune the irrelevant nodes, completely replacing the default graph expansion. After that, configure your multipath evaluation, make sure you're logging those aggregation weights for your audit trails, and finally, build automated verification pipelines. These pipelines will flag any paths that break your known domain boundaries way before they ever reach the end user.
There's also a very serious production warning from the researchers that we need to highlight here. Building these causal graphs can generate massive intermediate data structures. You absolutely must isolate these processes in a sandbox and strictly monitor your memory usage during path aggregation. And this is a hard rule. Never, ever expose those raw, unsanitized causal graphs to your end users. Those intermediate nodes might contain sensitive or completely unverified associations, and you do not want those going public.
The complete methodology, along with all the juicy benchmark details, is up on arXiv right now under paper number 2607.15281. It is a wildly fascinating structural rethink of how language models can actually handle complex what-if questions without just falling back on implicit guessing. So, as you review their modular pipeline, I want to leave you with this question. Given the massive, growing demand for transparent and reliable AI, is it finally time to ditch the black box and bring explicit traceability into your own application? Thanks for hanging out with me for this explainer. Keep building, and I'll see you in the next one.